Okay.
How's it going, everybody? Hey, Shane, what's up, buddy?
Hey Jay, how
Good.
are you?
So, for those of you who are tuning in here on YouTube, uh, oh, there we go. I'm getting. Oh, you know what? I've got audio in the background. Haha. Hang on one second. Let me shut all this stuff off. This is the joys of going live, folks. How's it going? We are here on the AVB podcast. Some of you may be tuning in on YouTube, on Facebook, and we are here with my good friend, Mr. Shane Miersch. How's it going, buddy?
Not bad. How are
Good.
you?
Sorry, technical difficulties as we're getting used to all this new stuff. Not quite used to the live streaming just yet, but thank you so much for joining us here. Uh,
Thank you for
so,
having me.
one of the funny things about going into this conversation with you today is you and I have been almost battling back and forth a little bit about how to put your title out. And I
Yeah.
sort of want to let's address that just a little bit because I think one of the hardest parts of all of this conversation is trying to filter out like who has credentials, what they're working on, what that really means in the grand scheme of all of this stuff as it comes together. So I'm going to shut up and let you sort of explain that part of it since you're the expert.
Sure. Yeah. Well, we went back and forth because initially you had put my title as being a vaccine developer, and that I am not actually. And so there's a distinction here that is very important to be made because I think the vast majority of the general public looks at this: when is the vaccine coming? When is the vaccine coming? Um, and that's a long, arduous process. So I'm going to make the distinction between a vaccine and a therapeutic. We're in the our interest, our objective here is to develop a therapeutic to combat this virus. That means it's intended to be used once an infection has already taken place, and its intent is for compassionate use to minimize the harshest effects of the virus. If we could tip the balance back from, okay, nobody dies from the virus anymore, or nobody goes into ICU anymore, that's a victory. That's a huge victory. On the other side, a vaccine is intended for people who haven't yet been infected. It invokes the natural immune system against the virus and essentially prepares you that if you were ever infected, that your body is immediately ready to combat that infection. The nature of the immune system, it's a complicated system, but one arm is the innate portion of the immune system, which is ready to act, but is kind of broadly specific. The other arm is the adaptive immune system. This is the one that takes some time to invoke. And essentially what the vaccine does is the vaccine invokes that, makes it ready so that upon infection, it's ready to go. It's ready to fight the virus immediately. And the likelihood of a viral infection taking hold and having dangerous physiological effects is minimized.
Okay.
So that's the cure that people like to talk about or like to speculate on. And the reality is, for instance, influenza. We've been combating this for hundreds of years and studying it probably for as long, but it's taken 50 years, and we still don't have a good vaccine that is broadly neutralizing against all the various strains. On the other hand, we see, for instance, in the case of HIV, studying this for 35 or so years, it's only now that they have the arsenal of drugs that allows them to clear an infection over time. So viruses are a crafty bunch, and there's no easy route here. So these are all going to be complementary ways of attacking this problem.
Okay. So I'm trying to find a way to take because everything you said is very very specific, and I think you in a lot of ways you have to have a bit of a background knowledge on a lot of this stuff. Is there a way for if you're not somebody who specifically spends a lot of time like digging into scientific studies and that kind of stuff, is there a way to sort of separate the idea of the difference between like you said the shot itself and just like how treatment factors work over, you know what I mean? Is there a way to sort of dumb it,
Yeah.
for lack of a better term, dumb it down?
Yeah, I guess the easiest and most succinct way is that therapies are intended to minimize the effects of an existing infection. A vaccine is intended to prime your immune system to be ready to prevent infection in the first
Okay.
place. That's
Okay,
yeah,
so I guess my question is, so like you guys are working specifically on therapies rather than vaccines, right?
yeah,
And is
exactly.
it, I guess my question is, why would, like, I know why it's important to work on both, but why is it that your team would be working on the therapies rather than the vaccines? Like what is it that you do that's different in your work, kind of thing?
Well, we kind of said this the other day that in light of the circumstances, in light of the crisis, that scientists have very quickly turned their attention to this. And we see the number of papers that are being published, the preprints that are being published. Everybody's attention is focused on this, but the reality is the major steps forward are going to probably come from people who are already doing something related and just simply apply their system to this particular virus. So, for instance, we are an antibody engineering lab. We The principal investigator of the lab has developed these antibody libraries. Essentially, these are in vitro libraries of millions to billions of antibody variants that we then have techniques for kind of fishing in and finding things that are complementary. So I guess if I wanted to kind of make it as intelligible as possible, I would have to take it back to, well, what is a protein?
Okay.
Right? I realize that in the general public there is a vast spectrum of understanding, from no understanding whatsoever to sophisticated understanding. And I guess if you didn't study biology in university, you might not have a solid understanding of what a protein is. So I guess what I would like to do is quickly take it down to first principles and then kind of expand upon that and bring it directly to the case of this virus and why we are targeting essentially what we do is we target proteins with antibodies. So a protein is a polymer of amino acids. We all know what amino acids are, right?
Well, no,
These are
that's not necessarily the case. Maybe we can explain that a
okay.
little bit.
Sure. So amino acids are one of the fundamental building blocks of life. Okay, we need them. We ingest them. Our body is made of proteins, large and in part, and these proteins are made of amino acids. These are the building blocks. I sometimes, when talking about this to people, I liken amino acids to Legos, and this isn't the best analogy, but it gives you a bit of an idea. Individual building blocks of a Lego can build a tall tower or a long, or any sort of structure with those. And in the same way, amino acids can be used combining with other amino acids to form proteins. So that's one way of explaining those. So essentially, a protein is a linear polymer of amino acids. There's a sequence. Each amino acid has its single letter sequence, and that reads very much like a sentence that has a message in it. That linear sequence of amino acids that form the polymer of the protein then dictates how that protein will fold in three-dimensional space. So proteins are kind of like semi-soft materials. It's not like a brick. It breathes, it kind of moves, and depending upon the environment, it can change shape radically. Okay. So we're really in the business of finding antibodies that are, I'm going to use a couple of terms here that I like, but really explain electrostatically and geometrically complementary to other proteins. And that's the fundamental basis for a molecular interaction. Things have to be, for instance, it's almost like a game of Tetris. If the two pieces are complementary, they fit together. If they're not complementary, they don't fit together. So we're looking at complementarity on a molecular level.
Okay. I think it does. I think I think in a way what you're sort of getting at is like at the chemical level, what you're working on is figuring out how to mix different components to kind of get them to do the things that you want. Is that essentially like, does that right? Okay.
Is complementary to it,
Okay.
right?
You know what? I'm going to get
Now,
you to go back because I think I did something on my end that people might have not been able to hear you. So I'll get you to restart that. So you're, yeah, I'll just get you to go back from the beginning of that. Sorry, well, I hope everyone, let me just break this for you for a second. Because just so everyone knows, I'm dealing with a bunch of sort of technical issues on this side while also trying to get all of the technical stuff of what you're talking about all at the same time.
sure.
So hopefully people who are watching, I'm not sure, there might be a bit of a delay on some of the audio, but that might also be my end. So as we're having some of these technical difficulties, and thank you, Justice, I just got your message. Feel free to talk in the chat. I will get these messages. So I'm sorry, let me go back to that and get you to start that over
Okay.
again, Shane.
Okay, so from the practical side of what we're doing. I said what we do here is we explore molecular interactions. We look for things that are complementary. We look for antibodies, which are a protein that are complementary to other proteins. In this particular case, with the coronavirus, the CoV-2 virus, we're looking at developing antibodies that are complementary to that virus and block its function. So of course, a virus is a particle. It's comprised of proteins, nucleic acids, sugars, and lipids. And we really look at the protein side of that. And it's known, actually, this is probably a good opportunity to bring this image up.
You want to do the shared screen? Hang on one second. I'll just pop that over.
Yeah,
Okay.
yeah,
Yep.
yeah. So I think everybody's seen, hopefully everybody's seen the images of the coronavirus where they've taken pictures of the virus at the atomic level with an electron microscope, and we see that kind of little ball with the little spikes that are coming out of it. Okay, so knowing something about the supramolecular structure of the virus is very important. But those spikes on the surface of the virus are critically important for the virus's ability to infect human cells. And so I have an image here. This is actually a cryo-EM structure. This is a way of looking at a protein at the molecular level to see what its structure is. And this is rich in information and what we use to essentially engineer antibodies that are complementary and specific. So we see this spike protein here. I can rotate it in three-dimensional space. This sits here at the bottom on the surface of the virus, and then you see this projects out. And what I'll do is I'm going to highlight. These are actually highlighted, but I'm going to kind of toggle them on and off. You see these here. These are regions of the spike protein on the virus that interact with receptors on the human cell.
The areas that you've got highlighted right there, those are the areas that connect directly with us as human beings, with pieces of us. Okay.
Exactly. Actually, I'm going to flip over to another image right here, and this shows that very same up here we see. This is what I've highlighted in this image here. This is what I was toggling on and off.
Okay.
Right? These are what we call the receptor binding domains. And these are exactly what interact with our human receptor. Now here's a structure. We see this receptor binding domain from the virus, kind of taken out of context of the spike protein. And the human receptor here, this is angiotensin converting enzyme 2. This is the human receptor on the surface of cells that the virus binds to in order to facilitate access to the interior of the cell. We'll go back to like early, university biology. Viruses are not alive. They are kind of this liminal space.
Oh, hang on. Let me go full screen on you. I want to hear this part. I want people to understand this part.
Yeah, so viruses are not alive. They inhabit this liminal space between life and non-life. They're a particle, and outside of the human body, they can't reproduce. right? So in order to reproduce, in order to proliferate, in order to infect an individual, they have to get access to the body first through the mouth or nose. And then once they're inside and circulating, they need to get access to human cells and to the interior of the human
Can I?
cell. And
Sorry,
it's,
sorry. I don't mean to
yeah.
interrupt, but can I think for a lot of people who are watching this right now, are you able to sort of go back to how the virus begins, like how it gets its start? Because like I know I don't want to get into the political side of man-made versus all of that stuff, but can you talk about what we know about how that virus is put together?
Well, you're talking about the origins of viruses on
Uh,
Earth, kind
Maybe.
of, because I think, well, now my expertise is in structural
Okay.
biology
If
and biochemistry, so we're getting a little bit outside of what I'm, my area of expertise. But viruses are ancient. They've been with us. There's theories that viral components ultimately were part of evolution that we took up and became, um, you know, part of the structures of our body. But viruses, coronavirus, it's been estimated that it's been around for thousands of years, variations on this. They evolve over time. But the important point to note is that outside the body, they don't
perfect. Okay.
reproduce. So as far as the origins from them, there's some people who like to think of, biomolecules from outer space that have come to Earth, and hot vents at the bottom of the sea that have kind of created this miasma that's conducive to the self-assembly of these particles. But that's really not, I'm more focused on the here and now, and what do we do about the
Gotcha.
situation currently. Yeah.
All right. So back to where we were at here. So
Yeah. So here again, we see in the light blue and the kind of teal color aqua, this is the human receptor ACE2 that the receptor binding domain binds to. And what I'm going to do is I'm going to toggle. We see this area right here. This is the interaction area. This is where all the business goes on. This
and
is where
that's part
one
of the virus, or that's part of the human receptor.
that is part of the
Okay.
virus. But you see how it kind of folds around here and actually looks like it fits on it, right? That's that's essentially that is an atomic, a molecular
Okay.
interaction. And this is what we are critically interested in, because you can imagine that if an antibody bound to this very region, it would block the interaction with the human receptor, right?
Okay.
Can you
Yep.
see that? If When this is free floating, when this is in this other structure that I showed, and the virus is trying to enter the human cell, if you had an antibody that blocked that interaction domain, that region there, then you would prevent infection. You would prevent internalization of the
Okay.
virus. And if you prevent internalization of the virus, then you prevent the reproduction, the proliferation of the
So what?
virus. And
So
you
what you're specifically working on is finding a molecule, for lack of a better term, that will adhere to that part of the human receptor, so that the virus itself doesn't have an opportunity to adhere to that. Is that correct?
Well, we're actually targeting things that not bind to the human receptor, but
Bind.
bind to the viral,
Gotcha. Okay.
yeah, viral site. Now, it's feasible that binding to the human receptor, and there are actually some advantages to that, because the human receptor doesn't mutate like a virus does. So if you block that receptor, you're blocking all the viruses that bind to that receptor, just regardless of whether or not they mutate. But then there's other caveats and potential toxicity. If you alter the function of that receptor by binding it, then you could be causing another effect. So currently, the strategy is to go after the viral side of things and block that. And I'm going to show another
Okay.
image here, actually. So this is that receptor binding domain. I've done the exact same thing here, where you see highlighted, and I can toggle this again, clickety click, like that. That is the region, again, that binds to the human receptor. Now, if I click this is actually the SARS-CoV, the original SARS back from 2003, the receptor binding domain from that virus. Now, this antibody, you can see here, this is the teal and green colored structure that I'm
Yep.
showing here, binds, this is another structure that's been gathered and solved for this, binds to the receptor binding domain. It doesn't bind exactly to that, but it binds enough, close enough to that receptor binding domain that it blocks that interaction between the viral receptor binding domain and the human receptor. So this is the sort of approach that we're taking. Of course, there's other ways of inhibiting the virus, inhibiting viral entry, inhibiting viral maturation, inhibiting some of the structural changes that occur when the virus binds to the cell, fuses, and that is taken up by the cell. But this is probably, in our opinion, the way in which we have greatest confidence that an antibody that has these characteristics will impede viral infection.
Now,
and there's been some work to support this with SARS. They can show that antibodies that block this site on the virus inhibit not only in vitro assays using just cells, but also in models, in vivo models. They've shown that it also can impede infection, lowering the virus titer. And this is the sort of thing that we want to do. If you can block infection, you can block the most dangerous effects. You can block people having to go to the hospital with any luck. You can block people from dying. That's the ultimate aim of this. Prevent those, prevent the progression of the infection.
Talk to me a little bit about, because I think the connection between SARS and this virus has sort of been talked about, but sort of explain to me and to the audience, how they're related, and also why specifically, like, talk about your connection to like the work with SARS and stuff as well, to sort of give people a path as to how this has led to where you're at right now.
Yeah, so there have been the coronavirus family is actually, there's 4 kind of subtypes, the alpha, beta, delta, and gamma. This SARS and MERS, these are beta coronaviruses, but there's also alpha coronaviruses that cause the common cold. And but of course, as viruses mutate in their natural habitat, in this case, they think that it's in bats, that it can evolve. And as it evolves, if the mutations that arise as a result of evolution provide some sort of fitness advantage for the virus, that mutation can then propagate itself. And essentially, that's what's going on. The virus, the SARS, what I'll call CoV-1 and CoV-2 are highly similar, especially in regards to that spike protein that I showed you. They're about 75% identical. In this receptor binding domain, as we can see here, if it's still up on the screen, I'll get rid of the antibody. So this receptor binding region right here, where we know that it binds to the human receptor, in this particular virus, this is the most variable region of the receptor binding domain. The rest of it is highly conserved. And this has important implications in drug design, because if you want something that would work for both SARS-2, SARS-1, and perhaps other coronaviruses, you really, you don't want to target necessarily the most variable region, because then, an antibody requires a very specific complementary target, or what we call epitope. And if there's subtle molecular changes in that epitope, in that region. Yeah, exactly. And this is what, this is part of the problem with flu and the drugs that they have for that, is that as it mutates, the old drugs don't necessarily work. And so really a lot of the work that's done in this is looking for antibodies that we say are broadly neutralizing. That is, they will neutralize multiple strains of the same virus. The hope, I think, most often is that it would neutralize all strains, but depending upon the nature of the mutations in a virus, it may be very difficult to do that. So the good thing about this particular coronavirus, the SARS-CoV-2, is that as an RNA virus, it has a relatively slow mutation rate, say compared to influenza or some other viruses. So, with regards to the development of therapeutics against it, with regards to the development of a vaccine, this actually bodes well. If the virus isn't mutating rapidly as it goes through the human population, the likelihood of finding something that will neutralize all strains containing subtle mutations is pretty good.
I know. I know. We want to get to talking about specifically some of where you guys are at right now. Before we get to that, I think it would be interesting, like even on a personal level, can you talk us through what your life has been like? I don't know, since February, or since when this started when this started popping on. Actually, when did it start popping on your radar? And then kind of talk us through the path that leads us up to now.
Yeah, well, so I actually have close collaborations with people in Shanghai. So this was on my radar immediately, actually, back in January when it became apparent what was going on. My colleagues, obviously, they're in China, started relaying some of the changes that were going on as far as the lockdowns in Wuhan, the changes in Shanghai, and kind of how that proceeded. So this has been on my radar almost since day one in various ways. We started working on this in mid-February. So the timeline, if we kind of draw the timeline of just to show how quickly this has moved, December 31st is when they first reported to the WHO that they had this cluster of atypical pneumonia cases that they weren't quite sure what it was. 10 days later, they published the sequenced genome from the virus isolated from patients. At that point, it became readily apparent of what we were dealing with, and that's when I think some of the alarm raised, because prior experience with SARS and MERS, we know that these are highly contagious and have the potential for causing pandemics. So mid-February, actually, I went to Brazil on a vacation. I think I got it in just in time, thankfully. And basically, just before leaving for vacation, we submitted a grant to start working on this. This was part of the emergency funds that the Liberal government had put in place to spur research into this area, and spur in particular applied research to developing therapeutics and vaccines to counter this. So I left, I think, on the 15th of February, was writing the final portions of the grant as I was getting ready to fly to Brazil, sent it out as I was leaving the airport, or just before I left the airport, and then
the joys of all of these businesses.
Yeah, it's not a joy, but a necessary evil, I suppose. So, but a week later, I received news that we were awarded one of the grants. Actually, no, a week later, we were notified that of 43 applications submitted, they funded 5, and we were ranked 6th. Oh. A couple of days later, they opened up a new pool of money and said, okay, we're going to award the next set. So, and at that point, we did receive the grant. And we had started working on it actually prior to that already, just prior to that.
Do you know kind of what the other projects are that got granted by that initial 5 funding? Like, do you know what they're working on? Like, I don't know how your world works, if there's any communication that way or not.
Yeah, well, there are some. I noticed that on the University of Toronto website that there are a number of different researchers. Some of the researchers are more sociological researchers and looking at the effects of the lockdown, the psychological effects. There is an MD that is doing clinical studies. One of the ways that in a case like this, in which rapid clinical trials can be conducted, is by repurposing drugs that are used for other ailments, but have a mechanism that may be effective in the case of this. And so I do know that there is a doctor conducting clinical trials on U of T campus right now. Some of the other studies I can't remember off the top of my head, but I know nationwide there's other approaches as well. Like I know Saskatchewan, which has a large vaccine development center, they're working on it. I believe in Manitoba, where they have the infectious disease research institute there, they're also working on this.
It's just
So
the specifics I wasn't looking for. It's just I think it would be interesting for the general public to kind of get an idea of where their tax dollars are going when it comes to all of this stuff. You know what I mean?
yeah, well, another one of our collaborators, Samira Mubareka at Sunnybrook Hospital, she's working on the RT-PCR diagnostics. So she works with clinical samples all the time. She was one of the researchers that isolated the virus back within the last month or so. Yeah, everything has moved very quickly. But the one thing that I mentioned that I might want to talk about, and I do really want to kind of take note of this, is that the researchers collaborate. Modern science is a collaborative endeavor. It's increasingly uncommon to have to find a single researcher that has all the tools under their belt to conduct modern research independently. It's almost a rule now that you do what you're good at and you do it well and you do it carefully, but ultimately having collaborators who do the other portions of the project is absolutely essential. So right now we're working with Dr. James Reaney. He's got 25 years of experience working on coronavirus, and obviously he has a lot of the tools in his lab for working on this. He is a critical portion of this collaborative effort. We're also probably most likely going to be working with Samira. She has the isolated live virus. So having our antibodies tested in her hands is going to be a critical stage of the project. But it's also important to note that, on our side, we're not necessarily doing all the testing. We do the engineering, we do the preparation, we do some early stage testing, but when it gets to the clinical testing, that's in somebody else's hands. And to be honest, like scientifically, that's a good thing. It spreads it out and make sure everybody's on the same page. Does this work or does it not? Well, tell me. I'm agnostic. I want to see something work, but I want to ensure that it's reproducible and real.
Absolutely, and it also puts it in a position where, like, if I'm the person that's using the thing that you came up with, if it doesn't work, I don't care. I just know that it doesn't work. Right?
Yeah, exactly.
To a certain extent, whatever.
So, and then the reality is, we have collaborators both locally, nationally. We're working with some different groups throughout Canada, outside of Toronto, and we're also working with some groups internationally outside of Canada. And this is a wonderful opportunity for, goodwill efforts to develop something that works.
How's that been coming along?
We're moving quickly.
Yeah. So let's go back through your walkthrough, because we were walking through how your timeline's been.
Yeah. So we started working on this, I think it would have been mid-March, in which I first received proteins and immediately started working on them. Like the very day I got the handoff from our collaborator, came back to the lab and started doing our work. So what we do is we find ways of we mobilize these proteins, these viral proteins in this case, and then we take our antibody libraries, which are these kind of collections of billions of antibodies, and we expose them to that protein. And again, looking for something that it's just like a fish or a fishing hook. You find something that's complementary and you fish it out of the library. You wash away everything that doesn't bind, and then you go through this process. So that's been going on. Those were successful. We now have a large number of clones against this particular protein, the full spike, the receptor binding domain. We're in the process. Of course, they're in a format that is useful for selections and engineering, but they're not in a format that's useful for testing. So we basically have to transfer them from the how do I get not so technical here? We have to transfer from that format, the engineering and isolation format, to what we call the therapeutic format, the IgG, the antibody. And at this point, I think on Monday we'll probably be purifying antibodies, and then we start testing what works, what binds this protein as an isolated protein. Do we have something that we can control and recombinantly express? And does it bind the target that it's supposed to? So we're going to move very quickly now from isolation of our leads to characterization of our leads to find, well, which of these actually work? And it is a very agnostic. We put them through the test, and what comes out of that is like, that's it. That's our candidate. So once we have candidates, we immediately have to we have a deadline next Monday to ship them to another country where they will do the live virus testing and see what works. And if that works, then we start to move potentially into scale up and development. But that is, there's a lot there that we have to consider. Proteins are, we have to be able to express large quantities of protein, and we have to be able to express it in a way that is functional and stable. So sometimes there's some engineering that has to go on there to optimize the properties of the antibody. But I guess the one thing that I want to drive home here is that what we are doing, we are isolating human antibodies. These are virtually identical to what already exists in your body, what already acts as the molecular surveillance system for the for your immune system. And this is the identical molecule that will target and neutralize infections as if your immune system was functioning normally. So this is very, antibodies have been, I think the first therapeutic antibody was developed in the 1980s. And since then, there's been, literally hundreds of these produced for therapeutic application. Against a virus, it's a little bit of a different animal. Most of the antibodies that have been produced have been against for oncologic applications to treat cancer. Some of them are to treat inflammatory diseases such as rheumatoid arthritis. But in going to the case of using antibodies to treat viral infections, in some ways, we're going back to the days at the turn of the century where they would inoculate a horse with a bacterium or a virus, collect the serum, and then use the antibodies from that serum to treat the disease. So it's interesting how historically we started from this place of using antibodies and then kind of went, oh, well, we have antibiotics for many of these things, for at least the world of bacteria. But now, even in the world of bacteria, they're coming back to use antibodies as effective therapeutics as well.
I think you just answered the one question I did have, and that's like, ultimately when you're done creating whatever it is that you're creating to, like, the therapeutic for this, and that's how does it end up, like, what is it that, like, how do I get it so that I have it? It's a shot, like, it's not a pill, but it's an injection kind of thing.
Yeah, antibodies are not particularly amenable to taking orally. As proteins, they tend to break down in the gastric acid of the stomach. So that's not a way in which they are usually administered. There are new ways of administering them, but generally intravenous injection is the way that they are used. But again, antibodies have been shown to be stable. Their immunogenicity, because they're human antibodies, the immune system doesn't necessarily recognize them as foreign, so they're stable. And in the bloodstream, one of the great things about antibodies is that they have a long half-life. Even antibodies that your body produces generally can spend up to 2 weeks circulating before they're degraded and removed. So what that creates opportunity for is that with any luck, a single injection would be sufficient to turn the tide. Now to go back to your other question about, well, how do I get it? So I'm going to go back to where we are right now in the process of developing the antibody and kind of sketch out the long road ahead of us.
I was just gonna. It's funny because you kind of already answered the question, but I was gonna say to you, like, I want to ask you the question that people like me most want to ask, and people like you least want to answer, and that's like, when do you got our when do you got our fix pill?
I have to admit, another interview on breakfast television a couple of weeks ago, and it was very short, so I didn't have much time to get my point across or say much of anything, as in contrast to what we're doing here today. But the first question that the woman asked was, "How long before we can expect a cure?" And for a moment, I believe that I had the deer in the headlights kind of look on my face, where I'm like, "This is not really." This is not going to be a cure. This is a therapy. A cure is another, once a virus is in your body, it's not the easiest thing to cure. Um, yeah, the timeline for this, generally, a therapeutic antibody can take years to develop as well. But in the case of an antiviral, because you're not targeting a human protein, and there's certain stages of the development that you can kind of skip over, possibly. So, for instance, once we have candidate therapeutic antibodies that are going to be sent out for testing against in live virus assays, once we have something that shows efficacy, that is an antibody that is capable of preventing infection with this virus, then we look at developing that. So scaling it up, clinical trials, preclinical trials in which we have to look at, does this now work? We've shown in an in vitro assay that this works, but now we need to look at, does this work in the human body? You know what I mean? So there's many places in which the whole process can fall down and fail unexpectedly. But having had some experience in this now, we've got an excellent team assembled, and I'm pretty confident that we'll find something that not only works in vitro but also in vivo. So beyond the initial testing, as I said here, we also have to deal with the regulatory authorities that regulate therapeutics within Canada. They generally, in this situation, you want to engage them early, so they know what you're doing, they understand, and they communicate to us, well, what do we want to see? What demonstration do we need to see in order to approve a drug for this disease? So that is a long process, and will involve other people. When you start producing, gram scale quantities of an antibody, we don't have that capacity here. We produce milligrams up to maybe a gram, but beyond that, for manufacturing for clinical use and commercial availability, that's somebody else who will do that at like thousands of liters scale to produce. So it's a long road, but we've engaged the right people now, and we have a pretty extraordinary team. And what our hope is that we will have a fully made in Canada therapeutic antibody for this SARS-CoV-2 virus, hopefully into clinical trials within the next 6 months. That's our aim. It's a faster timeline.
I was just going to say, that's even on its own, it's already an incredibly quick timeline, right?
I don't think that this could happen, one, without the cooperation of the researchers on the team, and two, without the cooperation of the regulatory authorities. We have to work together to find a way forward so that we have something that is both safe and effective. So that's where we kind of are right now. We're going to start shipping next week and doing the initial in vitro assays, but as soon as we've identified something that works, then we want to get that into preclinical and clinical studies as soon as possible.
We've been talking a lot of science here. Let me get the human side of this. How excited are you to be involved in all of this right now? Because I know you are. I can, despite the fact that you're exhausted, and I can tell that, just in the conversations we've had along the way, you're super excited to be dealing with this, right?
I absolutely am. I've been doing this, I said, I've been aiming for this. I think when I left college, In college, I studied primarily chemical engineering, organic chemistry, inorganic chemistry, polymer chemistry, industrial chemistry. And as I was finishing up in my third year when we were doing organic chemistry, I'm like, this isn't actually that interesting to me. But the drug design side of it, the drug design side of organic chemistry was very interesting. And then when I got to university and started studying enzymology and biochemistry, I'm like, wow, this is where it's at. Okay, let's, I have the desire, I was interested in drug development at that time, but not sure exactly how it was all going to shake out. I had a long and winding path. But to come back to your original question, yeah, it's been, to be honest, my life hasn't changed substantially. The only unfortunate thing right now is that I don't have as many band rehearsals. I don't have any band rehearsals, so I'm just working all the time, which is, it's temporary. But the time that I spend in the lab here, it's very exciting to be leading this project and organizing. The entire university is shut down right now, so the only people on campus that have been given an exemption to work are those who are working directly on this. So I feel also at the same time extremely privileged to be here, continuing to working on this and having the opportunity to kind of hopefully contribute to this long, proud tradition at the University of Toronto of both good scholarship, but also real world application.
It's incredible to me because myself as well, driving truck, my wife working in retail, there's the term of essential services get thrown around. Boy, are there varying levels of that.
Yeah. Yes, absolutely. I'm glad that we've had this opportunity to see who the truly essential services are, and it's not often the people that the overarching narrative says are essential. The people working in the grocery store, the people driving bus, the people driving truck and making sure that the fabric of society doesn't break down during this time. So I truly appreciate that, and I guess this is a good opportunity to shout out to all those people as well.
For those of you who are watching this as we go live, if you have questions, feel free to pitch them out on any of the chats. You can throw the questions up on YouTube, Facebook, the Facebook page, anywhere that you are watching this video. I'm looking to see as they come out. Mostly it's people being very kind and giving us helpful advice. Outside of that, there's no questions that pop up. But if they do pop up, I'll be happy to pose them to Shane. In the meantime, so it's funny because you're talking about how your life specifically hasn't really been hasn't changed much because of this, because you continue to work. And I wonder because I know for myself I'm really lucky, because if I had to be trapped in constantly, it would be bad for me mentally. And I know there's a bunch of people that are out there as well that are sort of trying to wade their way through all of this. And I know you see all of the same stuff that I see, in the public as far as Facebook and all of that stuff. I kind of want to get your perspective. Do you think your work that you do helps you mentally sort of walk yourself through our current situation? And do you, in layman's terms, not asking you as a doctor, but in layman's terms, do you have any advice for people that are sort of trying to figure out how to wade through all of the constant flow of information from varying directions on all of
this? Yeah. So 2 questions in there. Myself, definitely work is centering for me. I do spend a fair bit of time in isolation, studying, working in the lab. So yeah, definitely it's something that gives me, grounds me and keeps me motivated and looking forward. And I don't, I'm not sure that I'm in the place to provide advice to others, how to stay centered. Everybody has their own tactics, but as far as wading through the information that's being passed around, it's good to be critical. I've seen some, it's difficult because when you're talking about epidemiology and globally, there's a lot of assumptions made. There's limitations to what can be done, limitations to what can be known, and I truly believe that public health authorities are doing their best. But I also see a lot of things being passed around, and it's like to be critical, and my hope in doing this, in actually talking to you, other than the joy of simply sitting here and conversing with a friend, is to spread some measure of scientific literacy to the general populace, because I see some things that are just very, very concerning, because to me they can be obvious, but not necessarily to people that don't have the literacy behind them. And I think there's a lot of pressures on humans in the modern world. We have to be first and foremost emotionally literate. We have to be financially literate. So asking for scientific literacy is probably a stretch for the average person, but I will do my part to engage absolutely everybody I can, to wherever possible, stem the spread of misinformation.
Well, I mean, so far I think you've done a fantastic job. Is there anything that we should have gotten to that I haven't had the wherewithal through all of this to ask you?
I think you've done a pretty good job. I think we hopefully people will leave this talk understanding a little bit better, at least the difference between a vaccine and a therapeutic, and how they both will play a role in turning the tide against this. I'm confident that if not ourselves, I'm confident that we will come up with something effective, and hopefully get that to a place that is accessible to the populace. But I'm also confident that this will be dealt with in time, and will be dealt with in a rational manner. And I think that's where the criticality comes in, because there are changes that are being made, in the way that human life is organized. And I think we need to be very rational about that, and I guess push back in some ways on the overstepping civil liberties, and I those are important things too. I don't want to really get into that too much, but there have been other pandemics. There have been other very dangerous microbial infections that have ravaged the world, and we're going to get through this. I'm certain of that. But I guess if I had to do the hand wavy sunshine thing, I hope that what this situation with this crisis will teach us is what is truly important, and that we can't necessarily cut corners on things that are important.
We do have a question coming in for you, Shane, and you guys will have to excuse me, I don't have this set up, and my old man eyes aren't doing great at the reading, but we have a question here for Shane. Can you talk about the dangers of the public getting too hung up on the modeling that's going on? Seems like reality has not matched most projections.
Yeah, well, I think a lot of the initial projections were if people did nothing, if there was no response whatsoever. And I think as far as that, we can see, at least in Canada, I check. There's a website that I use to check the numbers on a daily basis.
Or is it a different one?
I think it's a different one. But it's nice to keep up on that. And of course, so not to get caught up in the modeling. Yeah, the models are often, imperfect, and there's a lot of assumptions there too. So we have to keep that in mind. And like I said before, the reality of epidemiological research is that there's a lot of assumptions, and as most data, the idea of perfect data doesn't really exist. So
well, there's the other thing too, is like statistical data analysis. Layman's talking here. I'm not a doctor of any of this stuff, but statistical data analysis, I think, is like, unless you're spending time kind of learning how to absorb those numbers and how to match them against each other, it becomes overwhelming, and you start looking at specifics and kind of not understanding how they work in relation to other things. And like those models that come out, you're looking at a model that has come to a conclusion that is one of a range of conclusions, and what they're giving you is the median. They're telling you the extremes, they're telling you the median, what's most likely to happen, like best case scenarios, and it's like those aren't predictions of what will happen. It's like, this is what we're looking at.
It's the range of possibilities. And to be honest, I think large and in part, public health authorities have done a pretty good job of communicating this when the substantial risk is. We know when community transmission started within Toronto, so that kind of at least changed my behavior. And okay, well, now I need to be increasingly isolated in this point. But I think, the modeling is I don't think it's a good idea to get too caught up into it. We know what the potential is for, and I think that is very real. But I think we also have, for the vast majority of people, actually adhered to the advice of the public health authorities, who are basing their recommendations upon evidence to the best of their ability. So, that's my position. I do trust in the public health institutions, even though they're not perfect, and even the testing process has not by any means been perfect. But I think a lot of this is going to come to light as, for instance, serological diagnostics come on board, and we know who has immunity to this and who doesn't. But it's a complicated, this is unfortunately the world we've created is highly complex, and having all the tools to really navigate it, it's not easy. And that's why I try to go out of my way to reach out to people, and where I can, where I do have the scientific literacy to break something down and to critically analyze and kind of lay things out in a non alarmist manner, I do that to the best of my ability.
And man, you gave a shout out and a thank you to all the frontline workers. I want to give a shout out and a thank you to yourself and folks like you who are working on this other front line of the battle. I guess not a front line, but I don't know. I'm mixing metaphors. I just want to say thanks, because you're doing an incredible job. And if it wasn't for people like you, who knows where we'd end up.
Well, I appreciate the encouragement, and I hope when we actually have something that is ready and available that, at that point we can celebrate.
Yeah, and any updates that you have, anytime you want to pop on here, even if it's, for a short talk, just to get out the information that we need to get out, make sure you let me know. We'll pop on and we'll do this again, brother. And barring all of that, I can't wait until I'm in Toronto or you're down here in Windsor and we're able to see each other face to face once all this is all over.
Absolutely. I think I've got a show booked at one of Tom's venues for June 20th. Crossing my finger that will still be a thing. That's maybe a little optimistic, but remember that date if everything's back to normal or proceeding back to normal. We'll have a drink.
All right, brother. All right, folks. Thanks for tuning in. If you have questions and stuff, if you're seeing this after we've gone live, feel free to go ahead and throw them down in the comment section as we go through. If something pops up that I can send over to Shane, then I will, and I'm sure hopefully Shane you'll be able to answer some of those maybe.
I'd be happy
great.
to.
Okay, folks, thanks for tuning in. We love you. Stay safe, stay home if you can, and let's get through this together. See you, folks.